Welcome back. We're going to talk for a moment about observations and inferences. Let's observe this white powder in a dish. When observing this powder, you will pay close attention to it in order to gain more information about it. You would use your senses to experience it. You may measure it, you may describe it, you may look at it in qualitative versus quantitative terms. When you observe something, you're doing it for yourself, so you're using your own senses to observe the object, in this case, this white powder. Having observed it, having engaged with it, having looked at it, you would conclude that the substance is white, and you would conclude that the substance is powdery. This would allow you to come up with a hypothesis as to what the powder might be, and you would go on then to design experiments to try and determine what it actually is. So this is the process that a scientist would make when observing something. But if you didn't observe it for yourself, say for example you were looking at existing data that described this powdery substance, you can still infer something on the basis of the evidence that's presented to you. In the case of an inference, you're doing it in your head. So you're not actually observing it for yourself, you're using your head to come up with some sort of an inference. In this case, you're going to use logic, reasoning, and the evidence to interpret or explain what was observed. And again, this is being done on the basis of your knowledge, what you already know. So in this case, you might actually say something along the lines of, I think this could be sugar. It might be sugar. And that would be an inference. If we take it one step further, we can look at the difference between induction and deduction. So if we were to define it using the dictionary, deductive reasoning, shown on top, begins with an idea. It makes an inference based on a widely accepted fact or a premise. If a beverage is described as drinkable through a straw, you would use deduction to determine soup to be a beverage. On the other hand, inductive reasoning, on the bottom, is making an inference based upon an observation. So in this case, you would be making an observation on the basis of a sample, and that would give rise to then the development of hypotheses and theories. So ideas and observations are the premise for induction and deduction, respectively. Let's talk for a moment about experimental design. Once you've identified a question and you've generated a hypothesis, you will need to design experiments. And experiments have several characteristics in common with one another. So typically an experiment will begin with defining your variables. So it's the first thing you must do. You will start by defining your treatments, what the variables are that you are taught to influence the response that you're interested in measuring. You would also need to consider the controls, and these are variables with no influence or no predictable influence on the response that you're measuring. And the last thing is, what is the responses that you're actually measuring? How would you measure responses that are needed to answer your experimental question? So these are the variables. These are the things that would vary for your experiment. Other considerations that are important are sample size. So on the basis of the experimental design, you would need to choose a sample size that would help you generate data that reduces error or minimizes error. So if you had a sample size of say 1, you could only say that something's true for a single individual. That's why when sample sizes are considered, they need to take into account the nature of the experiments that you're going to perform. Two other factors include randomization. We randomize during experimentation to try and reduce bias, and we replicate to ensure that the results are actually reproducible. So randomization, replication are incredibly important parts of any experimental design process. So when you've defined your variables well, and you have sufficient sample size, you've minimized error through randomization, and you've ensured that you can replicate your experiments, you should have experimental design that would allow you to measure the significance of your findings and your results. So these are the components of experimental design. Models and simulations also play a very important role in science. What is a scientific model? It is a mathematical or physical or conceptual representation of a system of ideas, events, and their processes. So if you look along the bottom of the screen here, we can see in the bottom left, this is a representation of a molecule. The second is a representation of the structure of a flower. The third is a representation of fish, and they are excreting into their tank. And the last one is a representation of the digestive tract and the digestive system. And this shows organs, how they relate to one another in the system. These are all models, as we would classify them. But in addition, you have simulations. And what simulations do is they imitate the behavior of a system, entity, phenomenon, or process through the exercise or use of a model. So simulations make use of models. This example on the left-hand side is by Edmund Helmer, and it represents herd immunity and how vaccinations at different rates would impact the spread of a disease. In this particular case, real data was used to generate this simulation. Models can also be used to make predictions on the basis of data, and such predictions can then be used to recommend interventions or guidelines and to inform policy. And this is an example from IHME, which shows predicted deaths from COVID-19 given scenarios such as vaccines being rolled out or mandates being eased. And if you want to go to this website, there are lots of examples of existing models and data that you can use to inform yourself about the COVID-19 pandemic. Replication and reproducibility. So in order to increase reproducibility and reliability of experiments, studies often involve multiple samples or replicates. If the predicted outcome is observed for each sample or observation, then the results can be determined to be reproducible for that individual. So in this particular case, you're swabbing this individual 3 times. Each time you swab the individual, you would expect them to come back positive for a particular observation, or negative as the case may be. But given the fact that there is variation between individuals, experiments are often conducted with multiple individuals and replicate samples taken as before. So again, if the same outcome is repeatedly observed, results can be analysed and presented, and if the findings are true, your hypothesis can either be accepted or rejected, and over time, a theory can be developed to explain the why of the phenomenon under investigation. So this is the basis of replicates and using multiple samples and multiple individuals in a particular experiment. Let's pause here for assignment 2.